Alright, let's have a look at topic 9, polygons. So we have already tackled 3 sides, right? And we have already handled 4 sides. When you have 3 sides, usually we call them triangles, and when you have 4 sides, we call them quadrilaterals, right? So why we stop here? So as shown here, figure 9.1, there are several different polygons, which are closed planar figures with line segments as boundaries. So all of the names of the parts of a general polygon are actually the same in the polygons we have learned about so far. For example, triangles and quadrilaterals. The segments that form the boundary are sides, which meet at vertices to form the interior angles. If we connect 2 vertices that are not adjacent on the polygon, then we can form a diagonal, such as diagonal AC in this figure here. And polygons are classified by the number of sides they have. Here are some names given to different polygons. You can have a look at that. When the number of sides is 3, we call them triangle. When number of sides are 4, we call them quadrilateral, and so on. Alright, then next let's have a look at the concept of regular polygon. A polygon in which all the sides are equal and all the angles are equal is called a regular polygon. Actually, we have already seen 2 examples of regular polygons, right? Equilateral triangles are regular polygon, and squares are also regular polygon who has 4 sides, right? So here, figure 9.3 shows a few more regular polygons. And as with quadrilaterals, we will be focusing on convex polygons in this lesson, unless otherwise stated. Can you recall the meaning of convex polygons? Okay, we'll only focus on the concept of convex polygons, and we'll discuss their properties in this lesson, unless otherwise stated. This means the interior angles of the polygons are all less than 180 degrees. Any questions? Alright, then first of all, let's have a look at the angles in a polygon. So in this lesson, we explore not only the interior angles of a polygon, but also the exterior angles. Exterior angles are formed by extending the sides of a polygon. For example, here in this diagram, angle BAX is an exterior angle of the polygon ABCDE. Okay, this is called an exterior angle. And all these angles are the interior angles of the polygon. Are you clear? All right, so next let's have a look at a example which shows a property of the interior angles of a polygon. So can you find the sum of the measures of the interior angles of pentagon A, B, C, D, E without measuring the angles? Okay, when you finish, please give me your answer in the chat box, okay? Have you finished? Neil? Amber? Leo? If you finish, please give me your answer in the chat box. Yeah, that's a question. Why it's 540? How did you get that? We are trying to prove this rule, right? All right, let's have a look at the solution together. So we don't know anything about the pentagons, right? But we know plenty about triangles. Therefore, we could use diagonals to cut the pentagon into some triangles, right? We could, for example, we could connect A and D, and then connect point A and C. Then we have triangle ADE, triangle ACD, and triangle ABC, right? We know the sum of the angles in the pentagon is the same as the sum of these angles. 1, 2, 3, 1, 2, 3, and 1, 2, 3, right? So here, sum of these three interior angles is 180 degrees. Sum of these three interior angles is 180 degrees. And sum of these interior angles is also 180 degrees. This is what we have known for triangles, right? Therefore, the sum of the interior angles in a pentagon is 3 times 180 degrees, which is 540 degrees, right? You get that? And based on this, can you find a formula for the sum of the interior angles of a convex polygon with n sides? Again, when you finish, could you give me your answer in the chat box? Alright, let's have a look at the solution. So as we did with the pentagon, we can actually break the polygon into triangles by drawing all the diagonals from one of the vertices, right? Sum of the angles in these triangles equals the sum of the angles in the polygon. Therefore, all we have to do is figure out how many triangles we can form when draw the diagonals. So for example, if you have a convex polygon, then suppose this is a point A. How many triangles can you have when we draw the diagonals? We could let A be the common vertex of all of our triangles. So each side of the polygon, except the two sides, which is this side and this side, right? Connected to A, is the side opposite A in exactly one of our triangles. So there must be n minus 2 triangles formed, right? You see that? By drawing the diagonals. Because if you don't count these two exceptions, there are n triangles, and actually we can't use these two sides, therefore there must be n minus 2 triangles, right? And since there are 180 degrees in each triangle, the sum of the angles in an n-gon is just 180 degrees times n minus 2, or n1, or 180 times n minus 2 degrees, right? So this is a general formula for the sum of the interior angles of a convex polygon with n sides. Well, again, this is not a rigorous proof, but the result also holds if you write the rigorous statements. And actually, it's a little more complex to prove that this is actually holds true for concave polygons as well. So this is also true for concave concave polygons. So we have just proved this is true for convex polygons, right? And we're not gonna show the proof for concave polygons. If you are interested, you could just Google them by yourself, okay? And any questions, just let me know in our next class. Okay, so in a summary, we have the relationship between the sum of the interior angles and the number of sides for a n-sided polygon. The sum of the interior angles in a n-sided polygon is given by this formula, 180 times n minus 2 degrees. Therefore, the measure of each of the n interior angles in a regular n-gon is given by sum of the total angles divided by n, right? This is one of the most important property for the polygons. So have a look at the property here, and probably you want to write this down. Alright, if you don't have any questions, let's have a look at another example. Now we turn our attention from the interior angles to the exterior angles. So let's have a look at this example here. The diagram on the right shows the 10 exterior angles of a decagon. Find the sum of these angles. Again, you could not just assume all the exterior angles have the same measure. And again, if you finish, please give me your answer in the chat box, okay? Okay, and actually this is also true when the side is n. For example, if the side is n, we know that the sum of the exterior angles plus the sum of the exterior angles should be n times 180 degrees, which is 180n, right? Then the sum of the exterior angles is n minus 2 times 180, which is 180n minus 360 degrees, right? Therefore, in that case, for n-gon, the sum of the exterior angles is just 180n minus 180n minus 360, which is also 360 degrees, right? For n-gon. Did you get it? Therefore, we know that for a n-gon, the sum of the exterior angles is always 360 degrees. And in a summary, sum of the exterior angles in a convex polygon with n sides is 360 degrees. And of course, the measure of each exterior angle in a regular n-gon is 360 degrees over n. You get it? So this is what we have known so far for the interior angles and exterior angles. So let's try using our new knowledge about the angles of polygons with a couple of example questions below. First, could you find the number of sides in a regular polygon in which each exterior angle measures 182 degrees? Have you finished number? Any ideas? Well, let's suppose the polygon have n size. Then there are two general approaches we can take to this problem. You could use either the interior angle or the exterior angle, right? We know that if you use the interior angle, we know the sum of the interior angles is, well, because each interior angle is 172 degrees, then the sum of the interior angles is 172 times n, right? And we also know we have a formula showing that the sum of the n exterior angles in a regular n-gon is 180 times n minus 2, right? So on the other hand, we have n minus 2 times 180 degrees here, right? Again, we have one equation, one unknown variable n, so we could solve n, which means 172n equals 180n minus 360 degrees, and 8n equals 360 degrees. Sorry, I should not write the unit here. And therefore n equals 45, right? And on the other hand, you could also focus on the exterior angle. So another method we could use is, since the measures of each interior angle is 182 degrees, each exterior angle is each exterior angle is just 180 degrees minus 172 degrees, which is 8 degrees, right? And we know that the sum of the exterior angles is 8. Times n, and this equals 360, right? And therefore you could also solve n equals 45. Did you get it, Amber? Okay, good. All right, have a look at the solution here. Any questions, just let me know, okay? All right, if you don't have any questions, let's consider the next one. So there is a regular 15 gon. Can you find angle ACB, ACD, and angle ADE? Again, I'll give you 3 minutes to consider this question, and after that, we'll have a look at the solution together, okay? And if you have finished, you can give me your answer in the chat box. Alright, let's take a 10-minute break, okay? After that, we can have a look at this question here. See you in 10 minutes. Alright, let's continue. Have you come back? Alright, so first let's draw a diagram to illustrate the concept here. And actually, we don't have to draw all sides. Because we only care about ACB, ACD, and ADE, right? So let's say this is AB, and then BC, then CD, and then DE. So we need to connect AC, connect AD, and since the polygon is a regular 5-gon, then each exterior angle is 360 over 15, which is 24 degrees, right? And each interior angle is 180 degrees minus 24 degrees, which is 156 degrees. And if you consider triangle ABC, this is actually a isosceles triangle, right? Angle BAC equals angle ACB. So we know the interior angle is 156 here, right? Therefore, we know each of the base angles should be 12 degrees because the sum of the three interior angles is 180, right? Therefore, we know angle BAC equals angle ACB, which is 12 degrees. That completes the first question. And then next, let's consider angle ACD. So angle ACD equals angle BCD minus angle ACB. We know angle BCD is 156 degrees minus angle ACB, which is 12, and that gives us 144 degrees, right? Okay, and in order to find angle ADE, we need to find this angle first, right? If you know this angle, then using the interior angle subtracted by angle ADC, then you will get angle ADE, right? So is it easy to find this angle? Well, we could use some congruent triangles to help us with that. So if you connect B and D, then we know triangle ABC must be congruent. Triangle ABC must be congruent to triangle BCD, right? Because this side equals this side. This angle equals this angle. Both of them are just interior angles of the 15-gon, right? And this side just share the same side here, right? Can you follow me? Therefore, these two triangles are congruent. Then we know that this angle here is also 12, right? And this angle here is 12. And then this angle here must be 24. And here this angle is 156. And of course this angle here is 156 as well. And what else? We know this angle equals this angle, right? In the two congruent triangles, we have just oh, sorry. I think yes, because we have just proved triangle ABC is congruent to triangle BCD, right? Therefore, this side equals this side. Then they share the same side here, and this side equals this side. Then we can say triangle ABD is congruent to triangle ACD, right? Therefore, we could also prove this angle equals this angle here, right? Then we know both of them should be 12 as well. Then you can find angle ADC is actually 24, right? And then triangle ADE should equal the interior angle 156 minus 24, which is 132 degrees, right? Did you get it? Okay, so next we have seen all sorts of problems involving triangles and quadrilateral areas. You won't be at all surprised that we rely heavily on triangles and quadrilaterals when we find area of polygons with more size, which basically means we're going to have a look at the polygon area. For example, if we have a diagram shown here, can you find the area of pentagon ABCDE given the side lengths and right triangles shown here? Again, I'll give you 2 minutes to think about that, okay? And we'll have a look at the solution together. I'll give a hint. Usually you can break the complicated areas into more manageable pieces. For example, triangles and quadrilaterals. Okay, of course, if you have finished, please give me your answer in the chat box, okay? Alright, if you have finished, let's have a look at the solution here. So basically, we can connect BE, right? If you connect BE, you break the shape into two parts. One of them is a right triangle, which is very easy to find this area, right? So first of all, we know the area of right triangle ABE can be calculated by using 1/2 of one side, another side, and this gives us 3 squared 2 over 2, right? And okay, seems like BEDC is a square. Well, let's verify if this is true. Well, first we can find the length of BE, right? So length of BE can be given by 3 plus 6 here, which is 3, right? So as you can see here, CD equals D equals BE equals BC. So basically, BEDC is a rhombus. And the interior angles, one of the interior angles is 90 degrees. So basically, BEDC is actually also a square, right? And we know the area of a square is also easy to find. So the area of BCD is 3 squared, which is 9, right? And therefore we know the area of ABCDE is the sum of these two numbers, which is 9 plus 3 squared root 2 over 2, right? Any questions? Okay, if no questions, let's consider another question here. Can you find the area of a regular hexagon with side length 8? A regular hexagon has 6 sides, right? And because it's regular, so each side is equal or congruent. Something like this. Alright, have you finished? Again, we could start by breaking the hexagon into pieces we could handle, right? Since the angles of a regular hexagon are each 120 degrees, so the long diagonals like this can split each angle into two 60 degrees, right? So this angle here is also 60 degrees. Therefore, each of the little 6 triangles formed by drawing all 3 long diagonals is equilateral. So for a equilateral, if you know the side, of course you know the area of that equilateral triangle, right? The area of such a triangle is 8 square root 3 over 4, right? Which is 16 square root 3. Therefore, the area of the regular hexagon is 16 square root 3 times 6, which is 96 square root 3, right? You get it? And this example tells that many problems involving regular hexagons can be tackled by dissecting the hexagons into equilateral triangles. Any questions? All right, then let's see another one. Okay, can you find the area of regular octagon A, B, C, D, E, F, G, H with side length 4? Any ideas? Okay, let's have a look at the solution together. So a regular octagon has 8 sides, right? 8 equal sides. Basically shaped like this. And also note that the interior angle of a regular octagon is 135 degrees, right? Did you get it? And of course, this angle is also 135 degrees. So if you extend the two sides, well, let's call this point A, B, C, D, E, F, G, H. So if you extend A, B, and DC, they'll meet somewhere here. Let's call this point X. So we know this angle is 45 degrees. This angle is 45 degrees, and this is a right angle, right? And similarly, extend these sides. And each of the angles here is a right angle, and therefore we have a square X, Y, Z, W, right? Because this side equals this side, AB equals CD, and all of the sides here are equal, and all of these sides of the octagon are equal. Then xw equals wz equals zy equals yx, right? Therefore, x, y, z, w is actually a square. And then we know the area of w, x, y, z is actually wz squared, right? Can you find wz? Of course, we can find that. That equals wh plus hg plus gz, right? Squared. And we know that hg is 4. Then this side is also, ah is also 4. Then we know that wh is actually 2 square root 2, right? So gz is also 2 square root 2. So that equals 4 plus 4 square root 2 squared. And that gives us 48 plus 32 square root 2. And then we know the area of A, B, C, D, E, F, G, H should equal the square W, X, Y, Z subtracted by the area of 4 WAH, which is 48 plus 32 square root 2 minus WAH is 4 times 1/2 of 2 squared 2 squared, right? And this gives us 48 plus 32 square root 2 minus 16, and this gives us 32 plus 32 square root 2. Did you get it? This is our final solution. Okay, have a look at the solution here and let me know if you have any questions, okay? And if you don't have any questions, now let's turn to a more general problem of finding the areas of a regular polygon. So let's consider this example here. The center of a regular polygon is the point inside the regular polygon that is equidistant from all of the vertices of a polygon. Let the distance from the center of a regular n-gon to one of its sides to be k, and the length of each side of the n-gon be s. Can you find a formula for the area of the n-gon in terms of kn and s? Okay, let me draw you a diagram to illustrate the situation here. So suppose this is your n-gon. And you know the length of OP, which is k, and length of each side is s. So AZ is s. Can you find the area of the n-gon in terms of kn and s? And actually OP has a name. The distance from the center to the side of the regular polygon is sometimes given the name apotheum. From the center to its side, distance is called apotheum. Okay, I'll give you 3 minutes to think about this question by yourself, and we'll have a look at the solution together, okay? All right, have you finished? Okay, so we can cut the regular polygon into n triangles here by connecting the center to every vertex, right? So one such a triangle is OAZ, which is shown here. The altitude to side AZ of this triangle is distance from O to the side of polygon. And we know this distance is K here, right? So we have the area of triangle AZO is 1/2 of the length of AZ and length of OP, right? Which is 1/2 of KS. And the polygon consists of n such triangles, right? So the area of the n-gon is 1/2 of K times S times N, which can be simplified to NKS over 2. Did you get it? And actually you could use this as a theorem to find the area of n-gon. So let's make a summary here. So the area of a regular polygon is half its perimeter times the distance from the center of the polygon to a side, because n times s is actually its perimeter, right? Okay, have you finished? Okay, then let's put what we have learned so far together to solve some typical polygon problems. So let's have a look at another problem here. Suppose we have a pentagon ABCDE here. Diagonals BD and CE meet at point Q. Can you find the angle of BQE? Another typical angle chasing problem, right? Okay, first of all, if it's a pentagon, we know the interior angle is 108 degrees, right? And EDC is isosceles because this side equals this side. And then you could immediately find angle EDC and angle DCE, right? So angle DCE equals angle DEC, which is 180 degrees minus 108 degrees over 2, which is 36 degrees, right? And similarly, we have angle CDB is also 36 degrees, right? And therefore, angle CQD equals 180 degrees minus angle QDC minus angle QCD, right? You see that? Which is 108 degrees. Therefore, we have angle BQE equals angle CQD, which is 108 degrees because they are vertical angles, right? Any questions? Okay, no questions. Let's have a look at another one. Can you devise a formula for the number of diagonals in a polygon with n sides? For example, if you have a polygon here, it has n sides. How many diagonals can you devise inside the polygon with n sides? Well, if n equals 3, we don't have any diagonals, right? If n equals 4, we have 1, 2, right? If n equals 5, we could have 1, 2, 3, 4, 5, right? So how about in general, when you have n sides, how many diagonals can you devise inside the polygon? Well, let's have a look at the solution together. First we could consider a single vertex A, right? A is connected to two other vertices by side. That leaves us n minus 3 vertices to which A can be connected by diagonals, right? So from one point A we have n minus 3 diagonals. Since there are n vertices and each can be connected to n minus 3 others by diagonals, there appear to be n times n minus 3 diagonals, right? However, this counts each diagonal twice. Did you notice that? Therefore, you have to use this number divided by 2, right? Why it's used twice? Because once for each endpoint, right? So the total number of diagonals in the polygon with n sides is given by this formula. So you could also use this as a theorem, okay? All right, then let's see another question. ABCDEFGH is a regular octagon. Can you find the ratio of AE over BH? Any ideas? Okay, so note that BH is one of the diagonals, right? Is it congruent to AC? Length of BH should be equal to AC, right? This is very easy to prove. And how about CE? CE also has equal length with BH, right? And how about EG and AG? We could prove each of the lengths here is equal to the length of BH, right? Can you see that? Then actually ACEG is a square, right? Can you see that? Because you can find this angle here, you could find this angle, then this angle is 90 degrees, right? Okay, so basically you have a square and AE is actually the diagonal of that square, right? Did you notice that? So basically you are trying to find the ratio between a diagonal of a square to one of its sides, right? We know that ratio is square root 2, right? Because this angle is 45 degrees. If this side is x, then this side is also x, right? Then that side is square root 2x. So AE over BH is just square root 2x over x, which is square root 2, right? Any questions? Okay, then let's consider another one. In the star diagram as shown on the right, can you find the sum of these angles, A, C, E, G, and I? We could not assume the pentagon in the middle of the star is regular. It's not necessarily regular, but we could still find the sum of these the 5 angles. How we could do that? Okay, any ideas? Okay, so what we know here is sum of the interior angles of a pentagon, right? And if we can establish a connection between these 5 angles and the interior angles here, then probably we can solve this problem, right? So let's label these 5 angles here as A, B, C, D, E. Then first of all, we know in triangle, oh, let's use some letters here, B, D, F, H, J. Well, if you could consider this triangle here, A, E, H, if you consider this triangle, then we have angle A plus angle plus E plus angle uppercase E is 180 degrees, right? Actually, we have 5 such triangles that we can use. And if you consider another triangle, then angle C plus A plus angle G is also 180 degrees, right? Similarly, we have angle E plus angle B plus angle I is also 180 degrees. And angle G plus C plus angle A equals 180 degrees. And angle I plus D plus angle C is also 180 degrees. So if we could sum up all the 5 equations, then we could see that there is a sum of 5 angles, right? This will give us angle A, well, twice of angle A plus angle B, twice of angle A plus angle C plus angle E plus angle G plus angle I, and plus A, B, C, D, E, right? And this equals 180 degrees times 5 gives us 900 degrees, right? Again, because we know A plus B plus C plus D plus E is sum of all the interior angles in the pentagon, which is 5 minus 2 times 180 degrees. Sorry, which is 540 degrees, right? Therefore, we know angle A plus angle C plus angle E plus angle G plus angle I, which is a desired sum, right? Equals 900 degrees minus 540 degrees over 2, and this gives us 180 degrees, right? Did you get it? So as long as you have a star, the sum of these 5 angles equals 180 degrees. Any questions? Okay, if not, let's have a look at one last example. ABCDFGH is a regular octagon with side length 12. Can you find the area of ABDG? Again, we have a regular octagon. And we know the side length is 12. What is the area of ABDG? Any ideas? Well, actually, ABDG is a trapezoid. I'm not gonna write the proof here. You can try to prove this by yourself after the class. Okay, you can start from there. We could dissect the octagon into pieces we can handle, and we know altitudes of the trapezoid can often be useful, so we could draw diagonals AF and BE. These are each perpendicular to GD and FE. Again, I'm not gonna write the proof here. Try to prove this by yourself. It's not that difficult after the class, okay? You can prove AF is actually perpendicular to GD and B is actually perpendicular to GD as well. Since GD is parallel to FE, then we have angle FGD equals 180 degrees minus angle GFE, which is 45 degrees. So triangle GXF is actually 45, 45, 90 triangle, right? Therefore, we know GX equals GF over square root 2, which gives us 6 square root 2, right? Similarly, YD equals 6 square root 2. XYEF. So let's call this point X and Y here. Sorry, I forgot to label them. XYEF is a rectangle. So XY equals EF equals 12. Therefore, base GD of our trapezoid has length 12 plus 12 square root 2. This is the key to this problem. Before we go through tricky computations to get AX, we can note that by symmetry we have AF is actually equal to GD, right? Alternatively, you can also use HL congruence to show triangle AXG is congruent to triangle DXF. Therefore, we have AX equals AF minus XF, which is DG minus GX, which is 12 plus 6 square root 2. Therefore, we can calculate the area of ABDG, which is 1/2 of AB plus DG times AX. And this is 1/2 of 24 plus 12 square root 2 times 12 plus 12 square root 2, and eventually you will get a number like this: 216 plus 144 square root 2. Alright, so have a look at the solution here, and if you don't have any question, please find the homework and today's notes together with a video recording from Google Classroom. Okay, any questions, just send me a message or email, and I'll see you next time then.